Welcome back. The histogram of an image represents the distribution of the intensity values of the image. A normalized histogram actually can be thought of as the probability density function of a random signal. By looking at the histogram of an image, we cannot deduce the structure of the image, but we can infer whether the image is dark or light or has a small dynamic range. In many applications, the image is desired to have a histogram of a certain shape so as to, for example, be more easily compared to another image. The most frequently encountered shape of the histogram is that of a flat or equalized histogram, which means that all intensities in the image are represented equally. Such an image should also definitely have a more pleasing appearance. What we will learn in this segment is how to derive the point-wise operation that we need to perform on the intensity values of the image so that the enhanced image has a flat or equalized histogram. We'll also discuss local histogram equalization. So let us proceed with this interesting topic. We proceed next with histogram processing, focusing specifically on histogram equalization. An important quantity for an image is its histogram. It's defined as h of k equals the number of pixels with value k. So if I have an 8-bit image, the values range from 0 to 255. I can go and count how many pixels have the value 0, how many pixels have the value 100, that would be 8 of 100, how many have the value 255, and so on. So given an image such as this one, here is its histogram. The horizontal axis is k, the range of the intensity values. This is an 8-bit image, so 0 to 255. And on the vertical axis are the values of h of k. The histogram clearly tells me how the intensity values in the original image are distributed. So for this particular image, there are no small intensity values. Then there is a peak, a lot of intensity values around, let's say, 30. There's another smaller peak here, let's say at 60, and there are no intensity values higher than about this point, let's say it's 125. And this is no surprise. Looking at the image, is a dark image, a lot of small values and very few high values. So again, the histogram gives me the distribution of the intensity values in the image, and as a matter of fact, if I take h of k and divide it by the number of pixels in the image, then each value is less than 1. The sum of all the values, or the area under this curve here, is equal to 1. And we can think of, therefore, the histogram as the probability density function of the intensity values. So with respect to enhancement, the idea now is not to manipulate the intensity values directly, but to manipulate the histogram directly. I'm bringing this example, this contrast stretching example, back to put things in context now that we talked about the histogram. If you recall, we started with this image on the left, and then we realized that this is a dark image, and we defined the transformation shown here. We found the minimum and maximum values of this image on the left, and then we mapped them from 0 to 255 in the output image. So the transformation we applied, the linear transformation, is given by this curve, and this again is the output image. Now, while operating on the intensities one at a time, independently of the neighborhood, we were also clearly modifying the histogram of the image indirectly. So this is the histogram of the first image. Again, it's a dark image, so most of the intensities are concentrated around low values, and there are almost no intensities here at high intensity values. And with this transformation, clearly we expand the range of intensity values, so there are more bright values here, so we would expect that the resulting histogram of the processed image is spread out somehow. And indeed, if we look at it, it looks like this. So while the intensity values were stopping around 120 or so, here we see that there are now higher intensity values that were generated in the processed image. So with the pointwise operations that we covered so far, one has some evaluation of the image, like again this one is dark, and then defines a transformation to be applied on the image independently of the specific values of the image. With histogram processing, we are looking at the histogram of the input image, and then we are placing an objective on the histogram itself. We are saying, for example, that I want to transform the histogram of the input image to another type of histogram, or as we'll see, what is most commonly done, I want to equalize the histogram. I want to turn the histogram of the input image into a flat histogram. And then this objective will determine the transformation here that I should be applying on the input image to obtain the output image. So again, now the transformation is defined indirectly in some sense by processing the image through the evaluation of its histogram, and is not set kind of a priori by us that, oh, okay, I want this straight line to be applied to the input image. So this is a major difference between histogram processing and intensity pointwise transformation. At the end, with histogram processing, I'm also going to apply a pointwise transformation to the input image. So for example, let's say this transformation is the resulting one that I need to apply to the input image to get the output one. So with that in mind, let's proceed with some examples of histogram processing. Of the histogram processing approaches, histogram equalization is the most commonly encountered one. The objective in this case is to obtain an image with a flat histogram. This way, all intensities in the image are equally represented, or in probabilistic terms, all intensities are equally probable. There may be various reasons for requiring an equalized histogram. One is that we expect that an image with an equalized histogram, it will look better, it will be more pleasing. All intensities again will be equally represented, so there'll be low intensities and middle intensities and high intensities in the image. Another reason is that when I want to compare two images, it makes sense to first equalize them, equalize their histogram, so that then the comparison will be on an equal footing, will become meaningful. Here are the algorithmic steps we have to take towards this objective. The first step is to normalize the histogram. By doing so, as already mentioned, the values of the histogram become probabilities. I changed the notation slightly here. So P of x of I is the probability that the intensity x is equal to I, and this is equal to the number of pixels that have intensity I divided by the total number of pixels in the image, m times n. So this number is clearly less than 1, and more than that, if I add up all these probabilities, their sum is equal to 1. I sum up over the range of intensities here. The intensities range from 0 to L minus 1. So this is a probability density function. Then the algorithmic steps I have to take are, the first one is I have to form this capital P of x of I function, which is the sum of the probabilities from intensity 0 to I. So the value of P of x at I is this sum from 0 to I. This is actually a cumulative distribution function, and this is the function I will use now to perform this point-wise transformation of the intensities values of the image. So the transformation is shown here. X of n is the input image, so this is one intensity value, the intensity of the input image at location n, n1, n2, this is a vector. So for a given intensity, through this, again, cumulative distribution function transformation, I will obtain the value of the output image y tilde at the same pixel location n. And since this mapping will give me values between 0 and 1, there is one more step according to which I take the y tilde here, there's an extra parenthesis, and multiply it by L minus 1, so that again y of n now, the image with equalized histogram, will range from 0 to L minus 1. Let's try to get some intuition of why this transformation will work out. So let's take the first case when the histogram of the image is indeed flat. So here are the intensity values ranging from 0 to L minus 1, and this is the probability of each intensity value I. So all intensities are equally probable. So if I form the cumulative distribution function for this PDF, it's going to be a straight line, and this is 0, this is L minus 1, and this is 0, and this is 1, right? And after I multiply the values here, y tilde, by L minus 1, then the values again of y of n are going to range from 0 to L minus 1, and therefore the overall transformation will be the identity transformation. So as expected, if the histogram of the image is already equalized, I should not change anything, and therefore I should perform the identity transformation. Now let's look at an image that has a histogram that looks like this. This is again the normalized histogram, or the PDF. So this means that this is a dark image. It has high concentration of low intensity values and no high intensity values. This is the maximum value. And if I form the cumulative distribution of this, it's going to roughly look like this. This is 1, this is L minus 1 up here. So since there are a lot of values here, it's going to rise pretty fast and it's going to approach 1 and stay there because there are no values of high intensity. So clearly a transformation like this will take small intensity values and spread them out over all possible intensity values. So if I apply this transformation to the input image, then the resulting image based on this transformation is going to be obviously an equalized image, and is going to be brighter in terms of where I started. And finally, if I have an image that has a normalized histogram that looks like this, this is going to be a bright image. It has a lot of high intensity values and very few low intensity values, and in this case the transformation, the cumulative distribution function, will look, so let's say L minus 1 is here, roughly speaking it will look like this. So it's 0 down here and then rises to the value of 1. So according to this transformation, high intensity values here are mapped to low intensity values. So if I apply this transformation again to the input image, I'll get an equalized image. Since I deal with discrete values, I am not guaranteed that the resulting histogram is going to be perfectly flat. This is a result, however, that if we were to use continuous intensity values, we can prove then in a rather straightforward way that indeed using the cumulative distribution function as the pointwise transformation, one ends up with an image that has an equalized histogram. Now that we covered histogram equalization, let's revisit again contrast stretching and histogram equalization. So we start with this image here. We realize it is dark. We arbitrarily, in a meaningful way, decide that a transformation like this is going to help enhance this image. So in, out, 255 here, x min, x max of these images. So we apply this transformation, and this is the resulting image. I see more high intensity values here due to this expansion, due to this transformation. Now, while this is happening at the intensity domain, the story at the histogram, let's say, domain is that this is the histogram of the image we started with, and the histogram of the processed image is this one. With histogram equalization, we start again with this dark image. We first look at its histogram, and then we place an objective that the processed image should have a histogram that is flat. So we say that the processed image should have a histogram that looks like this. Based on this requirement, as we already explained, I'm able to find here the appropriate transformation, which is through the cumulative distribution function, as we saw. So roughly speaking, it will look like this. So this is 255 here. And after we apply this transformation, here is the resulting image. This is a transformation defined by us in an intuitive way, and this is a transformation that is defined by the data, the actual data of the image, through this requirement that the histogram is equalized. And as already mentioned, since we deal with discrete data, we cannot guarantee that the histogram is going to be perfectly flat, but it's a close approximation to that. As another example of the application of histogram equalization, let's consider the four images shown here. They could be characterized as dark, light, low contrast, and high contrast. Here are the corresponding histograms which agree with the characterization we gave to these images. So for the dark image, we see most intensity values are low, are concentrated at low values. For the light one, most intensities are at high values. The low contrast one has a small dynamic range from here to here, and the high contrast extends the values from all the range of intensity values. After histogram equalization, that's how the images look like. They're almost identical. They have, ideally, their histogram should be perfectly flat. As we mentioned, they're not perfectly flat. Actually, they're shown here, and they just spread the values all over the range of values. But again, since we deal with discrete intensities, discrete signals, we cannot guarantee perfectly flat histograms. We see that for the last image, the one we characterized as high contrast, the histogram was almost flat, and therefore very little change occurred at the histogram, and very little change occurred to the intensities themselves. These two images look very, very similar. So if we look now at the cumulative distribution function, or the transformation that was applied in going from these images to these images, then here are the transformations. So they're numbered. 1 corresponds to this image, 2, 3, and 4. So starting with 4, and in accordance to the comment I just made, this is almost the identity transformation. This is 0 to 255 here, and 0 to 255. So it's the complete transformation, right? The histogram was almost flat, therefore very little change took place. With 1 is the case I described earlier, so it's a dark image, and this is the transformation that will spread the low values to higher values. With the light image is what I described earlier as well. The histogram is concentrated at high intensity values, so it's this transformation that transforms the second image. And the low contrast is pretty much an example we had done earlier that goes through this transformation. It increases the dynamic range. It maps this range of values over here to the full range of the output value 0 to 255. So these transformations do not look that different from what we were applying before. However, again, the main difference here is that before we would define these transformations directly, we would provide some arguments that I need one to expand or to stretch the values or to compress them. But now these transformations resulted from the objective of equalizing the histogram, and therefore they're image dependent. They're not defined independently of the intensities of the image, but are a function, in essence, of the distribution of the intensities values of the image. There are instances in which it's desired that to enhance the details of an image over a small neighborhood. And in that case, we can adapt the global histogram equalization that we described previously to a local version of it. So as an example, here is the original image, and here is the image with its histogram equalized, the global histogram equalization we've been describing here so far. In this particular case, it's not clear if something has been gained by equalizing the histogram of this image. If, however, now we equalize the histogram locally, we obtain an image like this. So local histogram equalization entails the processing of 3x3 neighborhoods. So we take a 3x3 neighborhood, we find the mapping that will equalize the histogram in that neighborhood, but we only process the pixel in the center of this 3x3 neighborhood. Then we move this 3x3 window to the next pixel, and we repeat this process. So we see for this particular case there is quite a lot of information that is revealed that is not visible in the original or the globally histogram equalized image. So under each of these kind of square rectangular patches, you see that there are specific structures that are now revealed when I do this histogram, this local histogram equalization. So this is something to keep in mind, is a straightforward extension of the histogram equalization we just talked about. It is again adapted to the local characteristics of the image.